yesterday we have seen, that is units, then fundamental quantity, fundamental units, derived quantity, derived units, also two supplemental units, that is plane angle, solid angle. Today we are going to see conventions for the use of SI units. Conventions for the use of SI units. Conventions for the use of SI units. We will see one by one. First, unit of every physical quantity should be represented by its symbol. Unit of every physical quantity should be represented by its symbol. That means every unit should be represented by its symbol. Second, full name of a unit. Full name of a unit always starts with smaller letter, even if name is after a person. For example, 1 Newton, 1 Joule, etc. But symbol for unit named after a person should be in capital letters. For example, Newton, Joule, etc. See here, full name of unit always starts with smaller letter, even if name after a person. That means if the unit is named after a person, then if we have to write its full form, Newton, Joule, then it should start with small letters, N-J. But if we have to write the symbol of the same unit, then can be written in capital forms, capital N, capital J. This is the second rule. Now we will consider third rule. Symbol for unit. Symbol for units do not take plural form. For example, 20 Newton is right. 20 Newton is right, but 20 Newtons is wrong. Okay, this is the third rule. Now we consider the fourth rule. Symbol for units. Do not contain any full stops at the end. For example, we write here, suppose 25 kg is right, but 25 kg, this is wrong. Okay, this full stop is not necessary. Fifth rule, the units of physical quantities, the units of physical quantities in numerator and denominator should be written as 1 ratio. For example, meter per second square or meter second raised to minus 2 is correct, but meter per second this is incorrect. Then sixth rule, use of combination of units and symbols for units is avoided when physical quantity is expressed by combination of two. For example, we can write joule per kg Kelvin. This is correct, but joule per kg Kelvin, this is incorrect. Here, joule per kg Kelvin, but not like this. Joule, this is in full form. This is symbol. That is symbol together is right, but symbol, full form symbol, it is not correct. Then seventh, a prefix symbol is used before the symbol of the unit. For example, see here, 1 millisecond, we write like this, millisecond. 1 millisecond, that is, second is the symbol of unit, second is the unit, and milli, this is the prefix symbol. We write here 10 raised to minus 3 second, or we write, suppose, 1 microsecond equal to 1 microsecond, 10 raised to minus 6 second. Okay, and last rule, 8th rule, space or hyphen must be introduced while indicating multiplication of two units. That is, for example, we write here meter per second, it is written as meter second raised to minus 2, which is equal to meter second raised to minus 2, and not like this, meter second minus 2. That means here there must be hyphen or space in between two units, like this. These are 8 rules we will see again. Unit of every physical quantity should be represented by its symbol. That is, unit of every physical quantity must be represented by its symbol. Then full name of a unit always starts with smaller letter, even if named after a person. That means here see Newton and Joule, these are the persons, but we write here one small n here, small j here, 1 Newton, 1 Joule. But symbol for unit named after a person should be in capital letters here. N, J. For Newton, N. For Joule, capital J. Symbol for units do not take a plural form. Plural form. See here, 20 Newton, 20 Newton, but not 20 Newtons. Not yes, ns like this. Because yes means second, it may be second. That we write 20 Newton, 20, but not 20 Newtons. Symbol for units do not contain any full stops at the end. See here, 25 kg is right, but 25 kg here dot, this is not necessary. It is wrong. The units of physical quantities in numerator and denominator should be written as 1 ratio. Means meter per second square or ms raised to minus 2. Here space must be here according to this rule. Here there is a space, but not meter per second per second. This is incorrect. Use of combination of units and symbols for units is avoided when physical quantity is expressed by combination of two. See here, joule per kg Kelvin. Joule is J is symbol of joule, kg kilogram, K temperature Kelvin, but not like this. Here see, joule, Joule. This is full form. This is symbol. This is symbol. That means we can't write like this. Symbol and full forms together. Only symbols are together. A prefix symbol is used before the symbol of units here. Suppose we write 1 millisecond, m milli. Yes, second. 1 millisecond means 10 raised to minus 3 second. 1 microsecond, micro, 1 microsecond. This is symbol and this prefix. Also, I will give one example here. 1 millifarad means 10 raised to minus 3 farad, or 1 microfarad 10 raised to minus 6 farad. These are the units of capacitance. Okay, that means this prefix m, small m, mu, micro, milli, micro, these are before the symbol of units. Space or hyphen must be introduced while indicating multiplication of two units. Here, meter per second, meter second raised to minus 2. Here is multiplication. Here, space or hyphen is there, but not here. Together, ms raised to minus 2. Here, if you have not given space or hyphen, then it is wrong. This is wrong and this is correct. Okay, these are the rules or conventions for the use of SI units. Now we will see next article. We are going to see some definitions. Here we will see first measurement of length. Length is measured in meter, centimeter, millimeter, micrometer, like that. Here we have to define what is meant by 1 meter. 1 meter. We have to define the 1 meter. 1 meter is length of the path. Length of the path traveled by light. In vacuum. During a time interval of 1 upon, see here, this figure is important, 299,792 458 seconds. Okay, 1 meter is that length of the path traveled by light in vacuum during a time interval of 1 upon 299 792 458 here. That means this much 1 2 3 4 5 6 7 8 9, this much digits are there in, that is a fraction of this much amount of the second. In that second, path traveled by a light in vacuum, that distance we call it as a 1 meter. Are we right here? Suppose another definition, or 1 meter. 1 meter is length of 1 meter is length of 1650763.73 waves in vacuum of a certain orange red spectral line of krypton 86 here. This is another definition. 1 meter is length of 1650763.73 waves in vacuum of a certain orange red, here this length, orange red spectral line of krypton 86. That means here you have to understand this definition. Here suppose we consider this krypton 86 metal or material, then if we obtain its spectral lines, spectral line, what is meant by spectral, what is meant by spectra? First you have to understand this spectra. What is meant by spectra? Regular arrangement of spectral lines according to their wavelengths. This is the definition of spectra. Then spectral line means, here suppose you consider the visible light, then it consists of suppose 7 colors. Here we write like this, VIBGYOR. That means here we can suppose this is the red, this is the orange, this is yellow, then here we consider this is the green, here we consider this is the blue line, we consider this is the indigo line, and we consider this is the violet line, Then these lines, suppose you consider the sunlight, and if we view this sunlight through spectrum, or we consider any spectral instrument, then we can, or suppose we pass the light, if we pass this light through the prism, suppose this is the prism, then these lines get separated. That means we consider here we got, suppose I will show only 3 colors. We get here a red, and we get here violet color. Yellow color is the mean color. Okay, and these lines, and this, that is we consider here spectra, or we consider here dispersion concept. Dispersion, it is actually in the second section, but dispersion means that is separation of light according to their wavelengths. This is the dispersion. This phenomenon is in section 2, that is light. Then we consider what is the spectra, regular arrangement of spectral lines according to their wavelength. These lines we call these as a spectral lines. That means we consider here, suppose we consider our main definition, that is if we consider krypton 86 material, and if we obtain its spectrum, then orange red spectral line. Okay, in between this orange and red, here this spectral line, orange red spectral line of krypton 86. Okay, then if we consider this is a wave, if we consider this is the wave of krypton 86, you see here, wave, transverse wave, we can show like this. See here, this is the wave. Okay, this is the wave, this is crust, this is trough, crust, trough, crust, trough, crust, trough, like that. Okay, convex part we call as a crust, concave part as a trough, crust, trough, like this. And here we consider this is one wave. Okay, this one wave, and this wave, one wave have length, we call it as a wavelength denoted by lambda. Then if we consider krypton 86 material and its orange red spectral line, and if this is the wave of that spectral line, then 1650763.73 waves. Okay, that means that much distance of this much waves, that distance we call it as a 1 meter. I hope you all understand this. This is the definition of 1 meter. Okay, then we consider this is the standard SI unit, 1 meter we have defined here. This is the measure, this and this is used for measurement of length. Now we consider here, we have defined that is what is meant by 1 meter. I hope you all understand this. Now we consider here next article, that is measurement of large distance, or we consider this method as a parallax method. Here you see what is meant by parallax. Suppose this is our eye. Okay, and in front of eye, suppose here we consider that is we hold one hand in front of eye. This is our hand. Suppose you consider here 2 eyes. We will see here. This is one eye. We consider this is another eye. And suppose we hold our hand in front of our eye. Suppose this is the hand. Okay. Now suppose this we close this eye, then we close this eye. Suppose by closing this eye we view the hand. Then suppose we got one position. Now we open this eye now and close this eye. We view through this eye. Then we see the position of our hand. Then it is observed that this position slightly changes. You do that experiment. Suppose you are sitting in your study room. We consider one eye is open and one eye is closed, like this. Now say position changes. That means with respect to that object, its position, or we consider the position of that object changes, and that we consider this as a parallax. Okay, this we condition as we call it as a parallax. Then by using parallax method we are going to obtain we have to measure the large distances. See here, suppose we consider a distant star. Suppose distant star is there and we have to measure its distance from Earth. Then what we do here, suppose we consider a distant star. Then suppose we consider here that is this is the star, distant star, and suppose we consider that is by using parallax method we have to obtain its distance. Parallax, it is defined. Suppose I will write here parallax is defined. Parallax is defined as the apparent change in position position of the object due to a change in the position of observer. We have seen that is two eyes. That means we view object hand through one eye, we view the same hand through another eye. So that means observer changes. This is the parallax defined, that is as the apparent change in position of the object due to a change in the position of observer. Now consider 2 points. We consider, suppose, let me scratch this. Suppose we consider 2 points. Suppose this is point A, this is point B on the earth. Okay, we consider these 2 points on the earth. Suppose A and B, these are the 2 points. And suppose this distance, we consider this is the distance. This distance is small. We consider here this distance is very, very small. Suppose this is the planet. Then observe the same planet S at a time on by 2 observers A and B. We measure the angle ASB. We measure this angle theta. Okay, angle ASB equal to theta. Theta is very small, and AS is nearly equal to BS, and which is equal to, I will write here D. This distance also D, and AB is equal to B. Okay, this distance is B. Then theta is equal to, we can write AB upon D, which is equal to B upon D. Theta is equal to, where theta is measured in radians, theta in radians. Okay, then theta equal to B upon D, and therefore we write here B upon small capital D, and therefore capital D is equal to, we can write here B upon theta, and in this way large distance can be measured. I hope you all understand this. Thank you.